In this video, we're going to be continuing working through nuclear chemistry. Specifically, we're going to be talking about something called half-life. So half-life, which you'll often see with this lowercase t and the little half sign next to it, is the amount of time it takes 1/2 of a sample to undergo radioactive decay. So our example here, we have thorium, and notice it's undergoing beta decay to form this proactinium. How did I know it was beta decay? Just as a refresher, remember beta decay is when a neutron transforms into a proton and it emits an electron. So pretty quickly I can see that our amount of protons, that atomic number, increased by 1, but our atomic mass, that mass number, stayed the same. So that tells you lost 1 neutron, you gained 1 proton, so when added together they still equal the same mass. And then you emitted this electron right here. So let's say I have 80 grams of thorium. I went ahead and I just put 80 circles here. Those are going to represent our 80 grams. So for each of those little individual atoms, there's no way for me to know when it is going to undergo radioactive decay spontaneously. I can't predict that, but what I can determine is the half-life for my sample. So if I have 80 grams of thorium at the beginning, and I wait, specifically if I wait about 24 days, I will then have 40 grams of thorium. It doesn't mean the rest of it disappeared, but it converted into proactinium and emitted that electron. If I wait another 24 days, I will now have about 20 grams remaining. And again, if I wait another 24 days, I will now have about 10 grams of my original sample left. So what that tells me is that every 24 days, half of my sample undergoes radioactive decay. In this case, it's beta decay, but it can be any of those radioactive decays we've talked about. So this tells me that my half-life, again, that little t with the half fraction, is 24 days in this case. Now a half-life can vary drastically depending on what you're working with. If we look at this table on the right, notice here's that thorium we just talked about 24 days for a half-life. And this graph, or this table is nice. It also tells you it underwent beta decay and it gave off some gamma radiation. There's several other different kinds. For example, radon-222 right here only takes about 3.8 days for half of the sample to undergo radioactive decay. You'll find that some samples take minutes or seconds to undergo radioactive decay. Or in the case of uranium, spontaneously undergoing radioactive decay, 4.46 times 10 to the 9 years. So a very long amount of time. And then one I also wanted to point out, this carbon-14, it takes about 5.73 times 10 to the 3 years. Why does that matter? Often we use carbon-14 to do carbon dating on older, previously living objects. For example, trees or people at burial sites, things like the Egyptian tombs, they'll do carbon dating to figure out when were they alive, when were they placed there, kind of thing. So it's a very helpful thing to kind of be able to predict how long that half-life is so you can do those calculations back in time. Something else I wanted to point out, we have a graph right here. You'll often see these graphs used for half-life. What they can tell you is they can give you an estimate of how much of your sample is remaining. So notice we start with about 200 grams. Once half of that disappears, we're down to 100, about right there. And it looks like for whatever this sample is, it takes about 5 days for half of that sample to disappear or to be converted through radioactive decay. Notice we divide that by another half, about 50 grams remaining. That process has taken about 10 days total. And you can do that on and on. So for example, if you know you're about 26 days after the initial sample has been placed, you can do that calculation to find out what number that is, how much of your sample is remaining. So pay attention take notes if you need to, reverse this video if you want to see any section of it again, and then you'll answer a few questions on your own.